I know you watched that other video on balancing equations, but now you get to watch Norton's version of a video on balancing equations. Yay! This type of chemical reaction is one of those that you are absolutely, throughout the rest of this try, going to need to know because it just keeps coming back again and again and again and again and again. This is a combustion reaction. Combustion, you have to know these. Essential chemistry, chemical reaction. A combustion reaction always starts with some sort of hydrocarbon. There's other things it could start with, but for our purposes, I'm going to be nice and say a hydrocarbon or carbonate. Hydrocarbon. Hydrocarbon. These are molecules that only contain hydrogen and carbon, but because carbon's specialer, that's a word, it's always going to take carbon and hydrogen. The other reactant you could watch for in a combustion reaction are carbonates. 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 Carbonates always contain, I should have said hydrocarbonates. Yeah, I'm brilliant sometimes. Hydrocarbonates, yeah. Hydrocarbonates always contain hydrogen, see the hydro, carbon, see the carbon, and 8 means oxygen. So in a combustion reaction, one of these two guys will always be in the reactants. Well, in a combustion reaction, you can think of combustion as being burning. Well, you can't burn squat without oxygen. So your two reactants will always be some sort of carbon-based substance, and you burn them in oxygen every time. The reactants are those. The products, on the other hand, never change. For a carbon-based substance, your products will always be carbon dioxide and water. You must know this. Absolutely know this. So, a couple of things. First one is that side of the reaction is what we call the reactants. There's the things that are going to react together in a chemical reaction to produce products. Always, products on that side, reactants on this side. If I flip the equation around, the reactants stay on the left. Products are on the right. Always. Atoms get rearranged. That is crucial to a chemical equation. In a chemical change, which we write a chemical change by writing a chemical equation, the atoms are rearranged. Okay, there's some things you need to know. We've got some parts of a chemical equation. Parts of an equation. Well, the first part are the reactants, the stuff you put together. Those are on the left. Then we're going to have this wonderful little arrow thing, and that arrow thing we read as yields. I hope I spelled yields correctly. Hold on, let me check. Snap, I didn't spell it correctly. It's Y-E-I. That stupid I before E every time gets me. Okay, so reactants and the yields, products. Yields is another way you could think of as saying to make. So reactants make, or reactants produce. We treat the yield sign as if it were an equal sign. So whatever's on the left must equal whatever's on the right. And on the right side then we have products. Yay! Now there's some states of matter symbols. We've got S for solid. Good. If you don't know S means solid, you should probably write that down. And then we have L for liquid, and surprise, G means gas, and AQ means, no, it does not mean acid. So I'm going to write acid here, and I'm going to put a circle around it, and I'm going to line through it. Okay, if I see this circle with the line through it, that's worth bonus points on your paper. Yeah. Aqueous means dissolves in water. For instance, if I took table salt, do you know the chemical formula for table salt? Do ya? Do ya? Do ya? Okay, well, do you? I'm asking people in my room, do you? Oh, good, she does. It's sodium chloride. Yeah. Whoops, I wrote the C capital. Oh, I just was supposed to. Silly me. Need more coffee. NaCl. That's sodium chloride. And if I put it in water, surprise, table salt dissolves in water. AQ. So AQ simply means dissolved in water. Now, acids, to be an acid, have to be dissolved in water, which is why you find AQ after the word acid, but it doesn't mean acid. It means dissolves in water. Technically, it means aqueous. Write aqueous. It might be worth a bonus point if you show me later. Balanced chemical equations are strange because you have these coefficients, and the coefficients don't always look like what you would expect them to look like. Because on the left side, please notice on the reactant side of this problem, I have a coefficient of 2, of 1, of 3, and it equals 1. Yeah, that seems like some seriously messed up math. I get that. But in order to make a s'more, you clearly need 2 cracker squares, my recipe anyway, calls for then 1 marshmallow, 3 chocolates, and you get 1 product, 1 s'more. Oh, by the way, this would be a synthesis reaction. This is one of those things you're going to have to know what a synthesis reaction is, and a synthesis you always end up making 1 product. That's one of the clues to a synthesis reaction. There's more, I'll get to it. But the point is, notice the total sum of crackers here is 2. The total sum of crackers here is 2. The coefficients do not need to add to the same number of coefficients here, but the number of stuff does. See, here I have 1 marshmallow. Over here I have 1 marshmallow. Here I have 3 chocolate squares, 3 chocolate squares. It is a balanced chemical equation. I have another kind of funny little gotta erase all the ink. Here's another one for you. Pancakes! Again, another synthesis reaction. 1 cup flour plus 2 eggs, half teaspoon baking powder to get them to fluffy. You can make 5 pancakes with this. I don't know where the water went on this chemical reaction, but that's the basic idea. Kind of need water. Probably should have had some oil in this. Oh well, nobody asked me. Now, in a balanced chemical equation, notice your balance is balanced. Here we have methane, which is CH4, and here we have oxygen, which is O2. And this one's saying for every 1 methane, I'm going to need 2 oxygens. See, there's 2 sets of little balls. Yep, 2 oxygens. And this is going to make yields, carbon dioxide, and 2 waters. So notice we have 1 carbon here. We have 1 carbon here. 4 hydrogens. 2 times 2 makes 4 hydrogens. We have a total of 4 oxygens on this side of the equation, and here I have 1 and 2 and 3 and 4. That's why the balance is showing this equation as balanced. Now this one's kind of cool. Here we have one of those wonderful diatomics called hydrogen, H2. It's one of the big 7, don't forget, starts with number 7, nitrogen. One of the big 7, and it so shows we have how many hydrogen balls? Well, we have 3 hydrogen molecules. And when I add to that a nitrogen molecule, I can make 2 ammonias. Now those coefficients certainly don't add up. 3 plus 1 does not equal 2, but here I have 6 hydrogens. Here we have 2 times 3, that makes 6. Here we have 2 nitrogens, and 2 times 1 is 2. Yay, it's balanced. Let's see what else I have on these handy dandy slides. Oh, there's the actual way you would write it. In this case, the G stands for gas. Yeah, oh look, somebody got it over there. Yeah, good job. This one, same sort of idea. So what I want you to do with this one's for extra credit, so I want you to go through and figure out the coefficients for this one and show it to me tomorrow in class. Oh, well that was silly. I guess you don't get extra credit for it. I tell you what, extra credit if you can explain to me what those coefficients are. I'm trying here. Okay, another way to show you that this is balanced. If you look on the reactants, we have 1 carbon. All right, 1 carbon. We typically don't write the ones, but this is just to help you see it. And then we have 4 hydrogens and a total of 4 oxygens. On the product side, we have 1 carbon, 4 hydrogens, and 4 oxygens. 1 times 2 is 2, plus 2 times 1 is 2. That gave us the 4 oxygens. In a chemical reaction, this is crucial. This is a law. This is something you must know. Atoms are not created or destroyed. They're only rearranged. Know that. The law of conservation of mass says atoms are neither created or destroyed, only rearranged, which means in an absolute perfect world, if I start off with calcium chloride and sodium sulfate as my reactants, and I start the reaction and get it rolling, my products will weigh the same in a perfect world, and I don't lose any matter because, sometimes that happens. However, because, we drop stuff on the bench. But in a perfect world, what we start off with is exactly the same. Why would this be true? Well, because we don't disappear atoms. We don't just make them appear out of nowhere or make them go away. If you have exactly the same number of atoms on both sides of a chemical reaction, the total amount of product and the total amount that you started with will be the same. Now let's get down to business. We're actually going to balance. Warning, this one's probably the hardest one I have for you. Why would I do that? Well, just to show you, this is as hard as they get and they don't get harder. So I started off with this one. Didn't want to give you a feeling of false confidence or anything. Nope, wouldn't want that. Well, the first thing you need to do to balance a chemical equation is count the numbers of atoms you have. I call this taking inventory. All right, so a couple of rules. The first rule you need to know is you cannot change chemicals by changing the subscripts. Don't do it. Absolutely never do it. Don't. Don't do it. I really mean this. Really don't do that. Do not change subscripts. Against the rules. Okay, you can only put numbers in front of the molecules. These are called coefficients. I could put a number there, or I can put one there, or I could put one there, or I could put one there. That's it. Those are the only places I'm allowed to put numbers. So now we're going to put inventory down. So before you get to step 2, we should take our inventory. So we have carbon, we have 1 carbon, and hydrogens, well, we have 4 hydrogens, and oxygens, we have 3 of those. See, because there's 2 here and there's 1 there, so that makes 3. And then on this side, we have carbon and hydrogen and oxygen. Keep the order the same, otherwise make it crazy. And I'm so close to crazy, I don't want to do it again. So 2 and 1, oh, there we go, 3. Okay, now, for a combustion reaction, and this is combustion, make a note. Why is this combustion? Can you do a combustion? Do you recognize a combustion reaction? Well, in this reaction, we always want to balance the carbons first. Oh, look, they're done. Now I want to do hydrogens. Well, there's too many hydrogens on the reactant side, so let's go over to the product side, and I'm going to need 4, so I'm going to put a 2 here. So 2 times 2 makes 4 hydrogens, but that just messed up my oxygens because now I have 2 there, and I have 2 times 1 is 2, so I made 4 oxygens. Snap! Okay, fine, so I have to come over here. How am I going to get 4 oxygens there? Well, I can turn it into an algebra equation. See this 1 oxygen here? There's 1 plus 2 times some number of oxygens, and I have to have 4. That's this 4 right here, went there. Well, when I do that, I end up with 2x equals 3, and so x should equal 3 halves. Or 1.5 if you want, and 3 halves. Now, if you're sitting there going, you're not allowed to have fractions, Norton. Well, technically you're not. I mean, you can, but you shouldn't. So what number could I multiply this coefficient by, and this one, and this one, and this one, and get rid of that fraction? Well, if you said times everything by 2, you are right. So 1 times 2 is 2, and 3 halves times 2 is 3, and this becomes 2, and this becomes 4. Ladies and gentlemen, you are balanced. Let's try another reaction. Do you know what type of reaction this one is? Well, if you said it's combustion, yay! Yep, because we have a hydrocarbon being burned in oxygen, giving you carbon dioxide and water. Trust me, you'll need to know this. So first step is take inventory. Yes. So we have 3 of these, and we have 8 of these, and we have 2 of those. On this side, keeping carbon, hydrogen, and oxygen in the same order, we have 1 carbon and 2 hydrogens and 3 oxygens. Balance first the carbons. So we have 3 on the reactant side, so we need to put a big 3 there. So we end up with 3 carbons. Now I have to redo my stupid oxygens. So 3 times 2 is 6, plus 1 more gives me 7 oxygens. Oh, that looks fun. All right, on here we have 8 hydrogens on the reactant side, so I need to get 8 over here. How are you going to do it? Well, if you said put a 4 here, you were right. So 4 times 2 is 8. Now I redo my oxygens again. 3 times 2 is 6, plus 4 gives me 10. Oh, that's not bad. How are we going to get 10 oxygens over here? We're going to put a 5 right there. And we are now balanced. Try balancing this one on your own. But you might want a hint. Do you see that there's hydroxide here? There's actually a hydroxide on the reactant side. Oftentimes, if you see a hydroxide on one side and a water on the other, you can reimagine this water as being HOH. This HOH is hydroxide. Water is a hydrogen and a hydroxide hooked up, which is why I think water should always be written HOH, not H2O, but of course nobody asks me these things. But remember what I said, if there is a polyatomic on one side that appears unchanged because it's over there on the other side, you can treat it as a single thing. So here we have calcium, we have 1. Hydrogen, we have 1 because that's a hydrogen. And then hydroxide, we have 1 because there's the 1 hydroxide. Calcium on this side, we have 1. Hydrogen is 2, and hydroxide is 2. So how am I going to get 2 hydrogens on the reactant side? I'm going to put a big 2 there. So that gives me 2 hydrogens and 2 hydroxides. We're done. Okay, this reaction's kind of fun. It's called a double displacement reaction. I'll tell you a story. See, iron and chlorine were together, and sodium and hydroxide were together, and they all got into a big fight one night, and so now iron's hooked up with hydroxide, and sodium went and hooked up with chlorine. Yep. It's called double displacement. That's something eventually you'll need to know. Double displacement. Displacement. It's kind of like that show, Wife Swap. Double displacement. You know, wife swap, where, you know, the couples exchange like wives and see how a couple of weeks with a stranger works out. Yeah, see, there was like, you know, iron was with chlorine, but it dumped chlorine, and now iron is with hydroxide. It's almost like high school. It's like a big high school dating thing, especially when you're in a smaller high school. Yeah, okay. All right, so here we go. So we have iron, Fe, and then we have chlorine and sodium and hydroxide. Do you want to keep this together or split it apart? I'd keep it together because look, there's hydroxide over here. Keep it together, folks. All right, iron. 1, chlorine is 3, sodium is 1, and hydroxide is 1. Keeping the same order so as to minimize the crazies. OH. All right. So iron is 1, chlorine is 1, sodium is 1, and hydroxide's 3. Where do you want to start? It doesn't matter. I'm going to start with the chlorines. I need more chlorines on the product side. How am I going to get 3 chlorines on the product side? Yes, you're going to put a 3 here. So here we have 3 sodiums. And now I have 3 chlorines. All right, irons are good. Check. Chlorines are good. Check. Sodiums suck. Okay, how am I going to get 3 sodiums over here? Well, if you said put a 3 here, you are right. So we now have 3 sodiums, and how many hydroxides? You got it, 3. We are now balanced. What kind of chemical equation is this one? Well, if you said this is a combustion reaction, you're getting good. Make sure you know combustion. I can't say that enough. All right, you try balancing this one on your own and then go ahead and hit play and see how you did. Well, first let's take inventory. I have 3 carbons and I have 8 hydrogens and 3 oxygens. Over here I have 1 carbon and 2 hydrogens and 3 oxygens. Always leave the oxygens for the end. I guarantee by the time I get done messing with the carbons and the hydrogens, the oxygens will not stay balanced. Don't worry about it. All right, carbon. I need to put 3 here to give me 3 carbons, and that's 6 plus 1 more is 4 oxygens. So let's see, 3 times 2 made 6 plus the 1, yep, 4, 6, and I got 4, that's funny, 7. Let's do it again. 3 times 2 is 6 plus 1 more. That's 7. All right, now for the hydrogens. I have 8 on the reactants, so I need to get 8 on the product. So let's put a 4 here. 4 times 2 is 8. I do the oxygens. 3 times 2 is 6 plus 4 is 10. All right, how am I going to get 10 over here? You can't put a 5 here. Nope, because that'll give you 11. Well, look, I have 1 oxygen here. See that one? And 2 times some number has to equal 10. So if that's 2x, it's going to equal 9. So x is going to equal 9 halves. Aw, man, there she goes with the fractions again. I know that's what you're thinking. Well, how am I going to get rid of the stupid fraction thing? Well, if you said multiply everything by 2, you got it. So we're going to put 2 here. This one becomes 9. This one becomes 6, and this one becomes 8. You are balanced. If you don't believe me, you do the inventory. I guarantee it. We are balanced. These remaining slides, of course, are just ones offering you extra credit, so feel free to jot these down and balance them anytime you wish. And let me see them the next day, and I'd be more than happy to check them out for you. The next video we do will be going from words to equations to balancing.